In 2015, a photographer named Ralph Mirebs published a series of photographs online. Within hours, they had been shared hundreds of thousands of times. Within days, they were reproduced in every major newspaper in the world. Within weeks, they had been viewed by tens of millions of people who, until that point, had no idea that what the photographs showed even existed. The photographs showed the interior of a vast hangar in the Kazakh desert, a space so large that the far walls were barely visible from the floor. And inside that hangar, sitting on the concrete in near total darkness, were two space shuttles. Not replicas, not exhibits, not museum pieces carefully preserved behind glass and lighting. Two actual spacecraft, covered in dust, covered in bird droppings, covered in the specific gray film that accumulates only when nothing has moved in a very long time. They had been sitting there for decades. The hangar is inside the Baikonur Cosmodrome in Kazakhstan, one of the most historically significant and most closely guarded aerospace installations on Earth. Or it was once. By 2015, the perimeter security around building MZK-112, the shuttle assembly and preparation facility, had diminished to a handful of Kazakh guards monitoring a fence that was, in places, no longer entirely a fence. Mirebs and his colleagues entered through a gap. They walked across open steppe in the early morning. They found the hangar door either unlocked or removed entirely. And inside, they found something no one in the wider world had seen in any detail since 1991. The MZK-112 hangar was built to assemble and service the vehicles of the Soviet Shuttle program. At its peak of operation, it contained the full infrastructure for preparing the most ambitious aerospace project the Soviet Union had ever attempted. Overhead cranes rated for hundreds of tons, service platforms at multiple heights, assembly staging for a system larger than anything else humanity had ever planned to fly repeatedly to orbit. In 2015, most of that infrastructure was still there, rusted, frozen in position. Still. And in the center of the floor, in two separate positions, two white spacecraft, one of them largely intact, one of them crushed beyond recovery, waiting in the dark for a program that had not resumed in over 20 years. The obvious question, the one everyone who saw those photographs asked immediately, was this: how? How does the Soviet Union, a superpower that launched the first satellite, sent the first human into space, and matched the United States step for step through the most extraordinary technological competition in human history, how does that country build space shuttles and then simply abandon them in a hangar in the desert? The answer requires going back to a decision made in Washington in 1972, and it requires understanding what that decision looked like from Moscow.
On January 5, 1972, President Richard Nixon announced that the United States would develop a reusable space transportation system, a space shuttle. The announcement was framed in the language of economics and practicality: reusable spacecraft, lower costs per launch, regular, routine access to orbit, space as infrastructure rather than adventure. In Moscow, the announcement was read with different eyes. Soviet military and intelligence analysts looked at the shuttle's specifications, its payload capacity, its orbital maneuvering capability, its projected return mass from orbit, and they reached a conclusion that would drive Soviet aerospace policy for the next 2 decades. The Soviet military assessment was explicit. The American space shuttle was not primarily a scientific or commercial vehicle. It was a weapons platform disguised as a scientific one. The cargo bay, 18 meters long, almost 5 meters wide, could carry large weapons systems. The vehicle's cross-range maneuvering capability meant it could alter its orbital trajectory, approaching Soviet territory from unexpected directions at unexpected times. And then came the specific calculation that alarmed everyone who read it. The shuttle could theoretically make a single orbit pass over Moscow, deploy a payload, conceivably a nuclear device, and return to a landing strip in the continental United States in under 90 minutes. This assessment was almost certainly wrong. American engineers had designed the shuttle as a scientific and commercial vehicle. The cross-range capability existed for ordinary landing flexibility across different weather conditions. The cargo bay was intended for satellites, space station components, and research equipment. But it felt strategically logical to the Soviet military establishment. And once an idea feels strategically logical to the people controlling the budget, it tends to become policy. The Soviet Union decided it needed a space shuttle, not because it wanted one, because it was afraid of not having one. In 1976, the Soviet government formally approved development of a reusable orbital spacecraft system. The program was given a name, Buran, the Russian word for snowstorm. From the beginning, it was defined by a single directive: build something that can match the American shuttle, match its dimensions, match its capabilities, match its operational profile. The Soviet aerospace industry, already stretched to its limits by the military and the existing space program, was handed a project that would ultimately consume resources equivalent to the entire American Apollo program. A snowstorm was coming.
Before the engineering work could begin in earnest, the KGB received its own assignment. Within the Soviet intelligence apparatus, a program called Line T handled technical intelligence gathering. Its purpose was to acquire foreign technology by whatever means were necessary, means including theft. With the Shuttle program now a national priority, Line T was directed at NASA, at American aerospace contractors, at universities with shuttle-related research programs. The operation that followed was not dramatic in the way spy films suggest. There were no midnight break-ins, no action sequences. It was patient, methodical, and extraordinarily effective. Here is the thing about American aerospace research in the 1970s that the KGB understood better than NASA. Much of it was not secret. NASA was a civilian agency with an institutional mandate toward openness. Shuttle research was published in peer-reviewed journals, presented at international conferences, deposited in university libraries in report form. Defense contractors were more careful, but even they left material in accessible places. The KGB did not need to pick locks or bribe officials. They needed to read, carefully, systematically, and often through intermediaries who had entirely legitimate access to the material they were photographing. The American assumption that openness was strength turned out to have a specific vulnerability. Soviet intelligence gathered thousands of documents related to the shuttle's design, materials, aerodynamics, and systems. Thermal protection tile composition, avionics architecture, control surface configurations, propulsion system data. The material was processed through KGB technical analysis units, translated, evaluated, and passed to the Buran design bureaus. The engineers receiving this material sometimes knew exactly where it had come from. Sometimes they didn't. They used it either way. The result was a spacecraft that, on the outside, bore an unmistakable resemblance to its American counterpart. Place a photograph of Buran beside a photograph of the space shuttle. The resemblance is striking. Both have a delta wing configuration. Both are approximately the same length, 36 meters. Both have a similar cross-section, a similar nose profile, a similar general arrangement. Soviet engineers, when pressed on the similarity, gave a consistent answer. The resemblance arises from physics. There are only so many ways to design a vehicle that must survive re-entry at orbital velocities and land on a runway. This was true. It was also not the complete truth. The interesting part of the Buran story is not what the Soviets copied. It is what they looked at, understood, and chose not to replicate.
because buried inside the visual similarity of the two vehicles was a fundamental engineering decision that made Buran, in several important respects, a more rational system than the one it resembled. The Americans had made a structural compromise that would haunt their program for its entire operational life. The Soviets, having studied American research thoroughly, looked at that compromise and said, "We will not do it this way." The American space shuttle had three main engines mounted directly in the orbiter's tail. These engines, the Space Shuttle main engines, the SSMEs, were among the most complex and most powerful rocket engines ever built. They burned liquid hydrogen and liquid oxygen. They throttled, they gimbaled, they were, by any measure, engineering masterpieces. They were also extraordinarily expensive to maintain. Because they flew with the orbiter on every mission, they had to survive re-entry, landing, and then be disassembled, inspected, and recertified before the next flight. This made the shuttle system enormously costly per launch, and meant the orbiter itself was heavier than it needed to be, carrying engines to space and back when those engines were only needed for the first 8 minutes. The Soviet engineers made a different choice. Buran would carry no main engines. Instead, it would ride to orbit on top of a completely separate rocket called Energia, a vehicle powerful enough to launch Buran, or a space station module, or a military payload, or essentially anything the Soviet space program needed to place in orbit. The orbiter itself would be, in essence, a glider. It would reach space on Energia's power, perform its mission, and return to Earth on aerodynamics alone. No main engines flying on every mission, no expensive refurbishment cycle. The propulsion system would be expendable, because the orbiter, which was the expensive part, could fly again and again without carrying those engines back to Earth. It was, on paper, a more rational design. The man given responsibility for the Energia rocket was Valentin Glushko. By the mid-1970s, Glushko was one of the most powerful figures in Soviet rocketry. He had been designing rocket engines since the 1930s. Some of the most powerful engines ever produced bore his original signature on their design drawings. He had also spent decades in a legendary rivalry with Sergei Korolev, the chief designer who had launched Sputnik, sent Gagarin into space, who died in 1966 and left behind an empire that Glushko had spent years positioning himself to inherit. Now Glushko had his program, and his rocket would be something that made everything that had come before look modest. The Energia was something extraordinary. 60 meters tall, over 2,000 tons fully fueled, 4 liquid oxygen and kerosene boosters strapped around a core stage burning liquid hydrogen and liquid oxygen. Total liftoff thrust, approximately 35 meganewtons. For comparison, the Saturn V that sent Apollo missions to the moon produced approximately 34 meganewtons. The Energia was in that class, the most powerful operational rocket in the world when it flew. And, unlike the Saturn V, it was designed not just for one payload, but as a universal heavy-lift system, a rocket that could carry whatever the Soviet space program needed to lift for the next 50 years. The Buran program was not built without conflict. Soviet aerospace was a world of competing design bureaus, each with its own political protectors, its own institutional history, its own ideas about where the future of Soviet space should go. Valentin Glushko's bureau and Vladimir Chalamet's operation, another powerful designer with his own program and his own supporters in the Politburo, represented competing visions that did not always point in the same direction. The Buran program required these competing interests to be subordinated to a single national goal. This was achieved, as most things were achieved in the Soviet system, through a combination of political directive, institutional pressure, and the strategic suppression of objection.
Building Buran required a mobilization of the Soviet industrial system on a scale that was staggering even by Soviet standards. 1,200 organizations participated in the program across its lifespan. 72 ministries were involved in supplying components, materials, and expertise. Approximately 600,000 people worked on the program at various points: engineers, factory workers, technicians, construction crews, administrators. The cost has been estimated at the equivalent of 30 to 45 billion US dollars in modern terms. This is what a space shuttle costs when you build it from essentially nothing, with a workforce that has never built anything like it before, under a political deadline that cannot be negotiated. Re-entry from orbit generates temperatures that destroy most materials. The space shuttle had solved this problem with ceramic thermal protection tiles, thousands of individually manufactured ceramic shapes, each fitted to its specific position on the orbiter's underside, each capable of withstanding 2,000 degrees Celsius on one surface while remaining cool enough to hold in bare hands moments later. The Soviets had studied NASA's tile system through their intelligence channels, and then they had to actually manufacture 38,000 individually shaped ceramic tiles themselves, using a workforce and an industrial base that had never produced anything like them before. Each tile unique, each fitted by hand to its neighbor, zero margin for gaps. Here is where the Buran program went further than anything its American counterpart attempted. Early in the design process, the decision was made that Buran should be capable of fully automated flight, from launch through orbital operations to re-entry and landing, without a human crew, not as an emergency backup, as a designed primary capability. The space shuttle had never achieved this and was never designed to. Every shuttle mission required trained astronaut pilots to fly the vehicle. Buran's avionics and computer systems were designed from the beginning to fly the vehicle completely autonomously, making every decision, monitoring every system without any human input. This was an engineering challenge of an entirely different order of magnitude. Before Buran could fly in space, it flew in the atmosphere. A dedicated subsonic test vehicle, designated OKGLI, was built with 4 jet engines fitted in its tail, allowing it to take off from a runway under its own power, climb to altitude, shut down the engines, and glide back unpowered in a simulation of the final approach and landing phase of an actual shuttle mission. Between 1985 and 1988, OKGLI flew 24 approach and landing test flights at Yubileyny Airfield near Baikonur. Soviet test pilots flew it. Their reports refined the aerodynamic model that the automated landing system would use when Buran flew its first orbital mission. Soviet test pilots trained for years in anticipation of flying Buran on crewed missions. They had ejection seats designed for the vehicle, emergency abort procedures practiced to the level of instinct, hundreds of hours in simulators and in the OKGLI atmospheric test vehicle. And then they were informed they would not be on the first orbital flight. The decision to fly Buran's first orbital space mission as an unmanned, automated flight was not a reflection on their capability or readiness. It was a deliberate engineering statement. If the automated systems are designed to fly this vehicle without crew, the first flight will prove they can. That is worth more than a crewed first mission. The test pilots accepted this professionally. They also understood that they were preparing for missions that had not yet been authorized beyond the first one. Buran was built at facilities outside Moscow. It needed to reach Baikonur in Kazakhstan, approximately 2,800 kilometers away across terrain that made road or rail transport of a 36-meter spacecraft essentially impossible. The only viable option was air transport. The Americans had addressed this problem by modifying a Boeing 747 to carry the space shuttle on its back. The modification worked. The Soviets had no equivalent aircraft, and they were not in a position to acquire one from the Americans. So they built one. The Antonov A225 Mriya. Mriya means dream in Ukrainian. It remains the largest aircraft ever constructed, a wingspan of 88 meters, 6 turbofan engines, a fuselage reinforced to carry oversized cargo both inside and on its back, mounted to a reinforced dorsal spine.
It was conceived for a single purpose: to transport the Buran orbital vehicle from its manufacturing facility to Baikonur Cosmodrome and back. One AN-225 was completed. A second was begun but never finished. The aircraft that flew for 3 decades after the Buran program ended, carrying enormous industrial loads around the world, was destroyed on the ground at Hostomel Airport near Kyiv on February 27, 2022, during the Russian invasion of Ukraine. The largest aircraft ever built, constructed to serve a program that lasted less than a decade, destroyed in a war fought over the ruins of the state that built it. In 1989, after Buran's single orbital flight, the vehicle was transported from Baikonur to Moscow on the back of the AN-225 for a public airshow appearance. Photographs of that journey, the enormous aircraft carrying the white spacecraft through the sky over the Soviet Union, became some of the most iconic images in the history of spaceflight. They showed in a single frame 2 things that the Soviet space program had actually built and that actually worked: a spacecraft that had reached orbit, an aircraft capable of carrying it. Within 2 years, the program that had built both would effectively cease to exist.
November 15, 1988, Baikonur Cosmodrome. The Energia Buran system stands on Launch Pad Site 110. The Energia rocket, enormous, white at its core, with 4 orange-red booster casings, holds the Buran orbiter alongside it, like a passenger preparing to separate. The weather is cold. The step before dawn is complete darkness. The floodlights of the launch complex illuminate the vehicle against the black sky. 250 tons of spacecraft, waiting. There is no crew. There will be no crew. The vehicle will fly itself. The first launch attempt had been aborted at 51 seconds before ignition. A sensor failure. A cable on the launch pad had not retracted as commanded. The automated system detected the anomaly and stopped the count. The Soviets quietly stood down, corrected the fault, returned the vehicle to its prepared state over 48 hours, and came back to the pad. The countdown proceeded again. The automated systems reported nominal across every check. The flight management computer, the intelligence that would control every second of this flight, was ready. The clock ran down. At 6 in the morning Moscow time, on November 15, 1988, the Energia's engines ignited. 4 booster engines, the core stage engines, combined thrust of approximately 35 meganewtons pressing against the launch structure. The sound reached Baikonur City, 40 kilometers away, as a physical wave, a vibration felt in walls and in chests. The pad was engulfed in steam from the water suppression system. Then the rocket rose. Slowly at first, as anything this massive must move slowly even under this kind of thrust, and then faster, the exhaust plume widening as the atmosphere thinned around it, the vehicle accelerating into the dark Kazakh sky. The powered flight phase lasted 8 minutes and 49 seconds. In that time, the system accelerated from standing still on the launch pad to approximately 28,000 kilometers per hour, orbital velocity. The booster engines separated. The core stage burned to depletion and fell away into the atmosphere. Buran, the orbiter, alone now, fired its small orbital maneuvering engines briefly, adjusting, circularizing. 250 kilometers above the Earth, traveling at nearly 8 kilometers every second, with no one on board. Buran completed 2 orbits of the Earth. The first orbit, automated systems checks, telemetry flowing perfectly between the vehicle and mission control on the ground, every subsystem reporting as designed. The second orbit, re-entry preparation. The computers ran through their checklists. The orbital maneuvering engines fired to lower the orbit. The vehicle was pitched to the correct re-entry attitude, nose up, the thermal protection tile array on the underside facing forward and down into the approaching atmosphere. The crew, if there had been a crew, would have begun suiting up. Instead, the computers prepared themselves. Re-entry is the moment that separates a spacecraft from a fireball. The physics are unforgiving. At 28,000 kilometers per hour, even the thin upper atmosphere creates friction intense enough to generate temperatures of 2,000 degrees Celsius or more. The 38,000 tiles on Buran's underside were built to absorb that heat, to glow and radiate it away while the vehicle's structure behind them remained intact. They had been tested in labs, they had been tested on the atmospheric glider, but they had never been tested in the only environment that truly mattered. Until now. Below the heated tiles, the vehicle dropped toward home, and the radio went dark. The radio signal returned. Buran was on track. It was descending toward the runway at Ubalini Airfield. And then the automated systems did something that surprised even the engineers who had built them. Instead of flying the planned approach, the flight management computer detected a crosswind that exceeded the parameters for a safe landing on the planned heading. It recalculated, on its own, without consultation, without authorization. And it chose to fly a complete 180-degree course reversal, extending the approach and coming in from the opposite direction, directly into the wind. The computer had assessed the situation and made a better decision than the pre-planned procedure would have produced. The crosswind at the runway was 61 kilometers per hour. For a conventional aircraft, this is significant, approaching or exceeding the limits for safe landing in many categories. For a spacecraft the mass and size of Buran, descending unpowered, with no possibility of a go-around, it was an extraordinary challenge. Buran touched down at 9:24 a.m. Moscow time, 3 hours and 25 minutes after launch, 2 orbits of the Earth, an automated approach that deviated from its plan in real time, and it stopped on the runway centerline with 3 meters of lateral error. 3 meters. When American aerospace engineers and NASA officials received details of Buran's first flight, the fully automated mission, the unplanned course reversal, the precision crosswind landing, the response was, by most accounts, genuine professional admiration. The shuttle, across its entire operational career of 135 missions, had never once completed a fully automated flight. It was not designed to achieve this. Buran had achieved it on its very first mission. There's a specific kind of silence that falls when engineers recognize something they hadn't anticipated from their competitors. Not dismissal, not denial, just acknowledgement. In the Soviet Union, the flight was celebrated as the achievement it was. Pravda ran the coverage on the front page. Soviet television broadcast the footage of the launch and the landing. The engineers and technicians who had spent 12 years building toward this moment allowed themselves an exhausted, brief, genuine triumph. Gorbachev sent congratulations. Plans were announced for what would come next, a crewed Buran mission within 2 years, space station servicing operations, an expanded operational fleet. None of these missions were ever authorized. The celebration was already the epilogue.
The Soviet Union in 1988 was not the same country that had launched Sputnik in 1957. 3 decades of Cold War military spending, of an economy structured around strategic competition rather than ordinary productivity, of subsidizing client states and maintaining the world's largest conventional military, had created a system that looked powerful from the outside and was, in critical structural ways, failing from within. Gorbachev's reforms, glasnost and perestroika, were attempts to repair cracks that had been growing for a decade. The Buran Program required the economy to hold long enough for the program to achieve operational status. The economy did not hold. Between 1989 and 1991, the Buran Program's budget was cut by approximately 80%. Not adjusted, not reduced in careful stages,
cut by 80% over 2 years. This is not a budget reduction. It is a program being informed it will cease to exist, but given a slow enough death that no formal announcement needs to be made. Engineers were not replaced when they left. Contracts with suppliers were not renewed. Facilities began receiving no maintenance allocation. Equipment sat where it was last used. The second Buran orbital vehicle, designated 1.02, known to the engineers who built it as Ptichka, Little Bird, was 95% complete when the money stopped arriving. On December 25, 1991, Mikhail Gorbachev resigned as president of the Soviet Union. The Soviet flag was lowered from the Kremlin for the last time. The world's first socialist superstate dissolved into 15 successor states in the space of weeks. Russia inherited the majority of the Soviet space program's assets, facilities, and debts. The Baikonur Cosmodrome, where Buran have been assembled, tested, and launched, was now inside the sovereign territory of Kazakhstan, a different country. Russia would lease it. But the political will and the economic resources and the institutional momentum that had built Buran were now irretrievably distributed across a fractured successor system that had other problems entirely. The Buran program was officially suspended in 1993. Not canceled, suspended. The distinction mattered to the engineers who had given years of their working lives to it. Suspension implied the possibility of resumption. Cancellation did not. But the possibility was not real, and most of them understood this. The completed orbital vehicle, Buran 1.01, the one that had flown, was moved into the MZK-112 assembly hangar. The nearly complete Ptichka was positioned alongside it. The hangar doors were closed. The people stopped coming. The lights went off. In the early years after the program ended, the hangar maintained a security detail. Baikonur remained a military facility. Guards were present at the gates. The Buran vehicles inside were classified assets of the Russian Federal Space Program. The boundaries were monitored. As the years passed, the security thinned. Not through any formal decision to reduce it, simply through the ordinary deterioration of institutions that no longer receive sufficient attention or funding. Some guard positions were not filled when the occupants left. Some sections of perimeter fencing were allowed to deteriorate without repair. By the mid-2000s, security around the shuttle hangar was described by those who visited the area as, at best, inconsistent.
The MZK-112 Assembly and Preparation Facility was not built as an afterthought. It was purpose-designed for the Buran Program, one of the largest enclosed structures on Earth when completed. Its interior crane system was rated for loads measured in hundreds of tons. Its floor area could accommodate the entire Energia Buran system during assembly and servicing. The structure was designed for the extreme Kazakh climate: harsh winters, hot summers, heavy snow loads, significant temperature variation between seasons. It was designed to last decades. It was not maintained. By 2002, the roof of MZK-112 had received essentially no meaningful maintenance for approximately a decade. In May of that year, a combination of structural fatigue, material degradation, and accumulated load caused a section of the roof to fail. The failure was sudden. The section of roof came down. It fell onto the hangar floor. It fell onto the Buran 1.01 orbital vehicle, the vehicle that had made the program's single perfect flight in 1988 and had been waiting in this building, in the dark, for the 14 years since. 8 workers were inside the hangar when the roof collapsed. They were not cosmonauts or lead engineers. They were maintenance workers, the kind of people whose names do not appear in the program histories, who perform the unremarked physical work of keeping buildings standing. When the section of roof fell, it fell on them. All 8 died. Their deaths are recorded in the Baikonur accident reports.
They are not otherwise widely remembered. Buran 1.01, the vehicle that had made the program's one perfect flight, that had flown 2 orbits and landed itself in a crosswind with 3 meters of error, was destroyed in the collapse. Not damaged, not compromised, destroyed. The roof structure that fell on it weighed thousands of tons. The orbiter had been built to survive 2,000-degree re-entry heating. It was not built to survive being crushed by a collapsing building. What had been, for a few hours in November 1988, the most sophisticated automated flying machine in human history was cleared from the site as debris. Some components were salvageable. The vehicle itself was not. The second vehicle, Ptichka, was positioned in a different section of the hangar floor. The roof collapse was localized. It came down on Buran 1.01 section. Ptichka was in a different position. The roof above Ptichka's section held, not because anyone had positioned it for safety, not because a decision had been made to protect one vehicle over the other, because the structural failure happened where it happened. Ptichka, the little bird that had never flown and was never going to fly, was now the only intact Buran orbiter in existence, and no one, officially, was responsible for its care.
When a building is closed and unheated and unvisited, time performs its own engineering. Dust settles, slowly, continuously, accumulating at the rate of millimeters per year. Over 30 years, this becomes a measurable layer across every horizontal surface. Bird populations move in through gaps in the walls. Pigeons, swallows, others. They establish colonies in the steel superstructure high above the floor, and they produce the specific archaeology of biological occupation. Temperature cycles. Kazakhstan winters reaching -30 Celsius, summers reaching +40, stress every seal and every coating repeatedly. By 2015, the MZK-112 interior was a particular variety of ruin, not the dramatic ruin of fire or violence, the patient accumulating ruin of institutional abandonment. Ralph Mirebs had done urban exploration before. He understood the particular character of abandoned spaces, the deterioration, the strange preservation of ordinary objects, the way emptiness accumulates its own atmosphere. He was not expecting what the MZK-112 hangar contained. You can prepare yourself to enter a large abandoned building. You cannot entirely prepare yourself to walk into a space the size of an aircraft carrier's interior and find a space shuttle. His first photographs communicate something almost beyond description, the specific dissonance between the scale of what is there and the silence surrounding it. Something this large, this sophisticated, this intended for the absolute edge of human achievement, sitting in the dark, forgotten. Mirebs' photographs showed Ptichka in extraordinary detail. The shuttle's white tiles, coated in gray-brown dust, the layer giving the vehicle a ghostly quality, present but faded. The Soviet Space Agency markings on the wings and fuselage, still legible. The cargo bay doors, closed as they would be for a mission. The nose, the same curve as the American shuttle, but different in proportion, different in subtle detail, and stenciled on the body in the utilitarian font of the Soviet space program, Buran. The spacecraft that had no name in the outside world, photographed for the first time in any real detail, in the light of a headlamp after 30 years of dark. Some of Mirebs' most extraordinary photographs were not of the shuttle itself. They documented what surrounded it. The overhead cranes, capable in their operational days of lifting the entire Energia Buran system, frozen in their last positions. Control cables hanging slack, hooks rusted in the grips they had last been left in. Work platforms at multiple levels still deployed around where the vehicles had been serviced, deployed and left. A technician's workwear hanging from a hook on one platform, a technical manual open on a work surface, the ordinary objects of a workplace left by people who presumably expected to return. The specific archaeology of a program that simply stopped. Adjacent to the assembly floor, the hangar complex included a facility control room. By 2015, it had been stripped of its most portable and valuable equipment. Computers and display units removed in the years after the program ended, salvaged for other facilities or sold. What remained were the architectural ghosts of the equipment: mounting brackets, cable conduits, raised floor panels where wiring had run, and, incongruously, objects too specific or too bulky to have been worth removing. A chair, a technical logbook on a shelf, and on the wall, a calendar. The month displayed, November 1989, the last month anyone updated it. Subsequent explorers, Mirebs was not the last to enter, documented Ptichka in greater technical detail. The thermal protection tiles, despite the decades of neglect, appeared largely intact. These are extraordinarily robust materials, designed for environments far more hostile than a Kazakh hangar. The vehicle's internal systems had been partially stripped, avionics modules removed, cables hanging loose where units had been disconnected and taken. But the fundamental vehicle, the airframe, the aerodynamic surfaces, the cargo bay, the basic structure, was still there, 95% complete, still, after everything. Ptichka and the destroyed Buran 1.01 are not the only vehicles from the program to survive. OKGLI, the atmospheric test aircraft that flew 24 glide tests, was eventually acquired by the Technik Museum Speyer in Germany. It sits there today, the only Buran-type vehicle anywhere in the world accessible to ordinary visitors. Two other partially built orbiters, at various stages of completion, ranging from approximately 30% to more than half done, are stored at a facility outside Moscow. 5 airframes were built across the program's history. None of them ever completed a second mission. The AN-225 Mriya outlived its original purpose by more than 30 decades. After the Buran program ended, the aircraft was recommissioned for commercial heavy lift operations. It became the world's carrier of last resort, the aircraft you called when the cargo was too large for anything else. Wind turbine blades, industrial generators, humanitarian aid shipments to disaster zones. It flew to nearly every corner of the world. It became, in some sense, beloved, the kind of machine people traveled to airports just to watch operate. On February 27, 2022, it was on the ground at Hostomel Airport near Kyiv when Russian armed forces attacked. During the battle for the airport, the aircraft was destroyed. The largest aircraft ever built, created to serve a program that had ended 30 years before, destroyed in a war over the legacy of the state that commissioned it.
The MZK-112 hangar at Baikonur today occupies an uncertain position. It remains technically within the boundaries of the Baikonur Cosmodrome, which Russia continues to lease from Kazakhstan, though the lease arrangement has grown considerably more complicated since 2022. Kazakhstan has announced intentions to develop its own national launch capability from Baikonur. A new launch complex, Baitarek, has been in various stages of planning and construction for years. What any of this means for Ptichka, the spacecraft sitting in the hangar, is genuinely unclear. The options exist: restoration and museum display, transfer, or continued deterioration until nothing worth preserving remains. No formal decision appears to have been made. Ralph Mirebs' photographs accomplished something that the program's own engineers, its historians, and its official communications had never managed. They made the world care about Buran. The images circulated so widely that they functioned as a belated obituary for a program that had been allowed to simply fade without formal acknowledgement. In the years since the photographs were published, there has been renewed historical and academic interest, documentaries, articles, archival research. Not enough to restore Ptichka, but enough to ensure the story is no longer entirely lost. The Buran program proved several things. It proved that the Soviet Union, when it chose to fully mobilize its scientific and industrial capability, could match the United States in the most technically demanding field of the Cold War era. It proved that the engineering choice to separate the orbiter from the main propulsion system was rationally superior to the American approach. And it proved that a fully automated spacecraft, one capable of making better real-time decisions than its pre-programmed flight plan, was achievable in 1988 on a single flight, without crew, in a crosswind. These are not small achievements, they are extraordinary ones. But the Buran program also proved something else, something harder to celebrate. It proved that even the most technically sophisticated achievement is ultimately worthless if the system that produced it cannot sustain itself. The program was built from its beginning on fear that the American shuttle was a weapons platform, fear that the Soviet Union was strategically vulnerable. When that fear was no longer politically manageable, when the economy made sustaining the program impossible, there was nothing underneath the program except the momentum of things already built. Technical excellence without institutional sustainability is an extraordinarily expensive way to produce things that end up in empty hangars. The section of the MZK-112 roof that currently stands above Ptichka has been standing, essentially without maintenance, for more than 30 years. It was designed for the Kazakh climate. It was designed to last decades. But it was designed to last decades with regular inspection and maintenance that stopped when the program stopped. The Kazakh winter still arrives every year. The snow still accumulates on the roof structure. The summer heat still expands and contracts the metal. The temperature cycles continue. How long the roof holds is a question that is apparently nobody's formal responsibility to answer. The 600,000 people who worked on the Buran program did not know while they were working how the story would end. They knew they were building something extraordinary. They were proud of that. The engineers who solved the automated landing problem, who wrote the software that made the unplanned 180-degree course correction in a crosswind, the technicians who fitted 38,000 tiles by hand, the pilots who tested the atmospheric vehicle. They were working at the frontier of what human beings had achieved. Some of them are still alive. Some have spoken in recent years, after the Soviet Union's end made the oaths of secrecy less binding. They speak with the mixture of pride and grief that belongs to work that was completed and then abandoned, work that was genuinely among the best in the world, work that sits in a dark hangar in Kazakhstan, going gray. There is a symmetry in the Buran story that feels almost constructed. The program began because the Soviet Union was afraid the American shuttle was a nuclear weapons platform. It was not. The Soviets built their shuttle by studying the American design carefully, and in doing so, identified the American program's central engineering flaw and chose not to replicate it. The vehicle they built was, in certain measurable technical respects, more capable than the one that frightened them into building it. And then both shuttle programs ended. The American fleet retired in 2011, the Soviet program abandoned 18 years before that, and neither of them ever changed the strategic balance of the Cold War by a single degree. All that fear, all that engineering, the world turned as it always had. Right now, in a hangar in the Kazakh desert, is a space shuttle. It has been there for more than 30 years. It is 95% of a complete spacecraft, capable, in principle, of the same automated orbital flight that its sister vehicle achieved in 1988. Birds nest in the structure above it. Dust covers its windows. Its thermal tiles, still present and still technically functional, are coated in the gray accumulation of decades. No mission is planned. No restoration is funded. No formal decision about its future has been announced. The little bird waits in the dark. The roof holds for now. The years pass. The ghost shuttles of Baikonur are not a story about Soviet failure. They are a story about what happens when two of the most powerful nations in history direct all of their intelligence and all of their resources and all of their fear at a single strategic competitor, and in doing so, produce things they might never have built on rational grounds alone. The Buran program should not have existed by any normal engineering or economic logic.
It was built for the wrong reasons, driven by the wrong intelligence assessment, and abandoned when the political context that sustained it dissolved. And in its single flight on November 15, 1988, it produced a moment of autonomous precision, an unplanned 180-degree course correction in a 61 km/h crosswind, landing 3 meters from the runway centerline. Wrong reasons, right engineering. That combination, the waste of it and the wonder of it, held in the same machine, is what sits in that hangar in the Kazakh desert. That is what the photographs show. Every year, the Kazakh winter comes to Baikonur. The temperature drops, snow accumulates on the roof of MZK-112, the structural steel contracts, the load builds, and every spring the snow melts. The summer comes, the temperature rises again, the metal expands. This has happened 30 times since Ptichka was placed in that hangar. The roof has held 30 times. How many more times it will held is, as far as anyone can determine, not a question anyone with the authority and the budget to answer it has been formally asked to address. The little bird waits. The Buran program flew once, November 15, 1988. 3 hours, 25 minutes, 2 orbits, a fully automated landing in a 61 km/h crosswind, 3 meters from the runway centerline. No subsequent missions were ever authorized. Buran Orbiter 1.01, the vehicle that flew, was destroyed when the roof of MZK-112 collapsed on May 12, 2002. 8 workers were killed in the collapse. Buran Orbiter 1.02, Ptichka, remains in MZK-112 at Baikonur. Its condition is uncertain. Its future is undetermined. The Antonov AN-225, Mriya, built to carry Buran, was destroyed at Hostomel Airport, Ukraine, on February 27, 2022. The Buran program engaged 600,000 people and cost the equivalent of 30 to 45 billion US dollars. It produced 1 flight and a ghost that still stands in the dark, waiting for a mission that will never come.